Hello friends, we are again here today to discuss our gamma ray scintillation spectrometer which we started yesterday. I gave you a block diagram of gamma ray scintillation spectrometer in which first part was I explained you the scintillator or the sodium iodide crystal. So this is here we have sodium iodide deactivated crystal which is encased in the aluminum case, so it is hermetically sealed. No air can go inside, no moisture can go inside, and the gamma rays are falling on this side. Here we have magnesium oxide which is used as a reflector for light. Gamma ray falling on this, they have inside photoelectric effect, component effect of prayer production, and they finally produce large number of electrons of various energy. Electrons after photoelectric effect or component effect. So these electrons now move because all these sides are sealed, they can't go, so they come to this side. This sodium iodide crystal is coupled with this glass tube. You see the glass tube, I will explain you. Here we have optical coupling. This crystal and this tube is having optical coupling. It means no light is lost at this place or minimum loss. So light, that is scintillations produced by electrons inside this sodium iodide, those light flashes cannot go this side, cannot go this side, cannot go this side, they will move to this side. We have a glass plate here, and between glass plate and the sodium iodide we have a material whose refractive index is same as of glass, so that there is no reflection at the boundary, there is no loss of the light. Means we put some organic, some silicon fluid, we use DC200, or we also use Canada balsam. So Canada balsam or silicon fluid is put between the sodium iodide crystal glass plate and this glass plate. This glass plate and this glass plate, and medium is between these, they have nearly same refractive index. So this thing is coupled optically, means no light is lost or minimum loss of light at the coupling. This whole glass tube is called photomultiplier tube. Its name given because initially we have photons coming from the sodium iodide crystal, that is scintillations. So scintillations are multiplied in terms of electron charge. So it is called photo. Actually it is electron multiplier, but because we are producing photons, visible light, so they are being multiplied by indirect method. So it is called photomultiplier. Means these photons here, they fall on this photocathode. There is a photocathode made of some material which has large number of free electrons. So that when these visible light fall on this, they emit large number of electrons by photoelectric effect. This is not a nuclear photoelectric effect. This is the optical effect. Say visible light falling on the, say, it is maybe copper cathode, say copper oxide, or some other good material having large number of electrons. These photons falling on this, I have shown only one electron, but they emit hundreds, thousands of electrons. So electrons are now emitted here, and this has got a curvature, so that these electrons are focused toward this side. I have shown only one, for example, but there are several electrons. You can say here we have many electrons coming out from here, many electrons. They are focused to this side. This is the cathode, and these are called this D1, D2, D3, D4, D5, D6, D7, D8, D9 and D10. I have shown 10. These are called D1, etc. These are called diodes. here we have metal cathode. These are also metal, same, having large number of free electrons available, having very, very small binding. So these are metal diodes, D1, D2, D3. And they are also having curvature so that its focus is on this side. This focuses on this side. And this focuses on this side. So when an electron comes out from here, and remember that these successive diodes are connected with a high voltage power supply around 500 to 2000 volt. This power supply, high voltage plus, connected through a high resistance or maybe mega ohm of the order of say 1 mega ohm or 10 mega ohm. This can vary 1 to 10 mega ohm. This resistance R and this is the capacitor C connected here. This resistance R, one end to high voltage, other end connected here to the one electrode. This is known as anode. Green, finally this is the anode. And from here we have a resistance series. On this side it is earth, E, earth. This side we use resistances of equal value, R1, 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 R1. So this is the resistance beta. A resistance in series, many resistances. This resistance here having some potential drop because this will send a current because it is grounded. So if this is say 500 volt, you add all the resistances, you will get the current. So that current will give a IR drop here. So this diode is connected inside by wire here to the potential here, some potential. This then next resistance connected diode here. Next this resistance connected inside here. Next like this. So each diode is at has say equal potential difference, say of the 100 volt. It may be 500 to 2000. So suppose this is, for example, 1000. So we have 100, 100, 200, 300, 400, 500, 600, 7, 8, 9, 10, 11. Maybe so. This power, this may have 90 volt drop or maybe like that. Around 80 to 100. So potential, 80 to 100 potential. Each diode has got an equal potential difference. So this is at say higher, say 1100 or 1000. This may be 900. This may be 800. This may be 700, like that. So the potential difference at each resistance, because resistances are equal, so each diode is having same potential difference. But remember, if this is at 80 voltage or 100 voltage, this may be at 200 because 100 difference. Then this may be at 300, this may be 400 and so on. So each diode has higher potential, means they have an attractive field. From this to this there is attractive field. From this to this there is attractive field for negative charge because the potential is positive. So electrons here we have photons falling on this. So these electrons are, now you can say, photoelectrons. So these photoelectrons, I have shown one, it may be hundreds or thousands. These electrons falling on the first diode, because they get accelerated, they have this high potential difference, 100 volt or 80 volt. Electrons are accelerated towards the diode D1 and they get higher velocity, energy. So they strike with the higher velocity here, they remove more number of electrons. Maybe say each electron removes say 5 electrons depending upon the voltage and the speed of this electron. So each electron is multiplying by giving kinetic energy to these electrons and say 5 more electrons come. So that the multiplication takes 5 times suppose. So this one electron and second or third, all electrons giving 5, 5 and and then these are focused to the second anode which has same potential difference. So further acceleration, multiplication, this is attracted toward this, so more multiplication. In this way, at each diode having a potential difference of 80 to 100 voltage, number of electrons is increasing, so that finally here, after diode number 10, I have given 10 diodes, it can be 14 diodes, it can be 7 diodes, it can be 80 diodes. It depends upon what is the requirement. So, finally we have huge amount of electron charge collected at the anode. Anode is connected with the resistance here and this capacitance here. So what happens? Huge amount of the photons which are scintillations converted into large number of electrons. These large number of electrons, finally we have condenser, the resistance, the current will flow, the charge will flow through resistance. So this current collected, this is the constant current flowing by the high voltage to keep the potential difference, but this charge gives additional change in the current, change in the potential across the anode here. So this change in potential is known as the electrical pulse. What is electrical pulse? Electric pulse is the variation of voltage with time. So this was constant voltage, and here this charge collected here, and this flows to the resistance R, and gives a potential drop at this resistance. This potential drop passes as the electrical pulse here. So this is the electrical pulse, negative, so you can say of the voltage minus dV. This is the drop of potential. If it was it may be the potential drop at the resistance is of some millivolt order, very small, because the resistance is very high, no doubt, but charge is also high, but the potential, you see, potential is IR drop. So I may be say microampere, and then you can calculate the potential. This is a few millivolts, order of millivolts. So this pulse here produced, negative pulse here, this is a few millivolts. And this is, remember that this depends upon the charge collection. Charge depends upon the number of diodes. Number of diodes, and at each diode what is the multiplication. So you can say that if I want to see what is the multiplication, say M, multiplication M can be given by n to power n. What is n and small n? Capital N is multiplication at each diode. So at each diode, one electron is multiplied by 5. So this is, suppose, n is multiplication factor, and say I suppose that this is equal to 5. That one electron of having kinetic energy removes 5 electrons from the diodes, metal diodes. I am taking a rough number, say 5. And diodes number, this n is the small n is the diodes. Diodes number. How many diodes? I have shown you 10 diodes. So 10 diodes means small n is 10. It means multiplication m is given by 5 to power 10. You can calculate this value is about 10 to power 7. So it means, remember this multiplication is 10 to power 7. If one electron came from here, from the sodium iodide crystal photocathode, if one electron came, here we will have 10 to the power 7 electrons. So that way you can see how many electrons coming initially, and then you can say what is the charge finally. So many electrons here means huge amount of charge collected at the anode. And this anode, we know that we get a pulse, this electrical pulse, which can be further passed through electronic circuit, which I will explain you later on what we have after this. But this is the diagram of photo-multiplier tube with a fixed number of diodes. Number of diodes depends upon your requirement, and the power supply also designed for each tube. Power supply is given that this will operate between 800 to 1000 volt like that. So this I can now remove from here, that this photo-multiplier tube is multiplying photons converted to photoelectrons, and those photoelectrons coming out from the cathode, giving large number of electrons having equal potential difference, multiplying to diodes, and diodes multiplying to large number of electrons. Finally, we get huge amount of charge at the anode, and which constitutes a potential drop across resistance R, and we get electrical pulse. Remember this electrical pulse, I have a small expression for this, that from simulation tube I can get that V, the potential, or we can write V or dB, you can say anything, you can write dB or V. This potential dB is equal to dq over C, where dq is the charge and C is the capacitance. So what is the dq? dq is the charge, is given by electron charge E into, I can say, you can write by some symbol, say, and E, number of electrons produced finally, how many electrons are produced, and E is the electron charge. E is electron charge. Ne is final number of electrons collected at anode. So this dq is E and E, and the pulse is divided by the capacitor C. This becomes dV, dq over C, pulse I, dV. So what the Ne depends upon which factors. So I can write now, say Ne is given by, I have from empirical calculation that I write here, that Ne is given by EI A CIP TP and then G and the CPE F mu FD M over EP. Now I will explain these various terms, what these terms means. You see, any number of electrons finally collected. EI is the energy, initial energy of the gamma ray. EP is the energy required to produce photoelectron. So by this energy deposition, if per electron this energy is required, so how many photoelectrons are produced by gamma ray? And then this other factors you have say A is this A is probability of absorption of gamma ray energy by phosphor, that is the crystal, by scintillator, by sodium iodide. So what is the probability? Maybe 20%, 30%, not. So how much probability is that energy? Or what is the photoelectric effect probability? That means what is the component effect? So that is the A is the probability factor, that the gamma ray deposited energy by what interaction. So what was the probability of that interaction at that particular energy EI? So this probability factor. Then CIP is the efficiency of conversion of electron energy into photon, that is scintillation. What is the efficiency? TP is optical transparency. What is the transparency of the light scintillations at the photomultiplier or crystal junction? It is 100%, this can be 1, or it is 0.9, 0.95 or 0.8, whatever, depends how much light is lost at the coupling. So the TP is the optical transparency, how much light is transferred. And then G is the fraction of photon energy, falling on the photocathode. Then how much scintillations, total energy scintillations, say scintillations of say 3 electron volt, that's how much total energy of photons, whatever energy of that photon. What is the fraction of photon, total photon energy falling on the photocathode? All the photoelectrons are falling, or some missing, 80% falling. The photoelectrons produced at the cathode, whatever the photon energy. So how much energy is being absorbed by photocathode? All or refraction. So that G is that fraction. In this way, I can continue to say now what is left now? CP is CPF nu at the frequency. CPF nu is relative response relative response of frequency, photoelectron conversion efficiency. This is the photoelectron conversion efficiency. Well, what is the efficiency? How much the photons falling on the cathode, what efficiency they are being converted into electron? All 70%, 60%, 30%. So what is the photoelectron conversion efficiency? And the F nu is the relative response of frequency. Because photons are what frequency? Energy, so we have frequency. So that F, what is this total factor? Photoelectron conversion efficiency at this frequency. This changes with frequency also. And then M is the electron multiplication. Then I gave you n to the power n. That I calculated for 5 taking n approximately it was 10 to the power 7. So it may be like that, 10 to the power 7, 10 to the power 8, etc. It depends upon this and this also. So m is given that. In this way, you can write the value of Ne. Number of electrons finally produced, and we can get the pulse height from this. We multiply this E over C and this whole factor here and E. So we can get. Remember now, I add here a very important point. You see, this number and it depends upon so many factors which has got statistical variation. Something is constant, fixed. Say this is fixed number, energy required to produce photoelectron. This is fixed number. Then all other factors are having variation. Natural statistical variation. Sometimes there is the optical coupling may be 80%, sometimes it may be 79% or 81%. Because every phenomenon, natural phenomena has got statistical variation. So all these factors are having a variation. For one particular gamma ray just now came, this may be say number Ne may be suppose some number 10 to the power 9. For next it may be 0.8 to the 10 to the power 9. Because these all factors they have statistical variation. So this number Ne is not always constant. This has got an error. With standard deviation we take n plus minus under root n. Means everything has got statistical variation. So remember, this pulse height will also have a statistical variation. Though this pulse is produced by same number, same energy gamma ray, we were talking about the statistical variation, that each factor, these EI, leaving EI, leaving EP, all these other factors, they are having statistical variation. So due to statistical variation, the pulse height is not constant. Pulse height has got, if V is the voltage, then V plus minus dB. It may be, this was dB, you may write this as dB or V simply. V is equal to Ne over C. So this V has got a variation V plus minus dB. Means the pulse height is not only one particular value. There are pulses produced by this photon multiplier, tube and hole assembly having variation. So many, it means corresponding to one energy of photon, that is gamma ray, converted to photoelectric effect, you should get theoretically, what you should get? Theoretically you should get one sharp pulse, one sharp. I must get theoretically one sharp energy of E gamma, a voltage corresponding to this. No, but by statistical variations of various factors at multiplication, at optical transfer, at the diode multiplication, etc., we get these here variation in the pulse height. Pulse height may vary like this, for a small variation. So in place of theoretical one sharp, we get pulse like this. So we get not a sharp pulse, theoretically we should get only one height of this E gamma, but experimentally we get this variation. So this is called broadening of pulse height, pulse, or the pulse width. Remember that this pulse width is very important because this is connected with the resolution of the spectrometer, resolution of the detector. So this pulse width, that is say, if this I can say delta B or delta E, if it is energy axis, that E is the energy here, then this is the delta E. Delta E full width at half maximum. This is important factor, delta E. How much delta E? Because this gives the width of the electrical pulse. Because electrical pulses are of various height, so if you plot them energy versus height, you get a broad peak. So width of the electrical pulse, this much, delta E over E, this is a very important factor. Important factor connected with the resolution of a spectrometer. What the resolution means? If the delta is very large, what will happen? You will miss many other nearby pulses. If delta E is large, we say poor resolution. So in a good spectrometer, what is required is delta E should be minimum. Somehow broadening should be decreased. The broadening of the reason of broadening is statistical variation at various levels, starting from the photoelectric effect, scintillations produced, scintillations multiplication, photoelectron multiplication, each diode multiplication, then before that optical transparency, and then each diode multiplication, etc. Finally, so all these delta E depends upon so many factors, and hence the broadening of the peak. Broadening of the peak is inherent. We can't go away from this. But we have to minimize somehow And that is the important thing in the nuclear physics, nuclear experimental physics, that we have to reduce this pulse width, delta E. Otherwise, poor resolution, we will miss many nearby gamma rays, because gamma rays will come within the all gamma rays here of this energy and this energy and this energy and this, they will come within this inside. So you can't see them, you can't resolve, you can't measure the closer energies. That is called resolution. So sodium iodide spectrometer spectrometer has poor resolution. It has poor resolution. But remember, resolution is poor, but it has high efficiency. High efficiency means because the photoelectric effect, etc., depends upon the charge of the crystal. So this has got cesium iodide, sodium iodide, iodine has got 53 Z, etc. So high efficiency means gamma ray detection efficiency is high as compared to other, but resolution is poor. So we have to compromise efficiency and resolution. Other detectors may have good resolution, but their efficiency is low. And I can give you now the latest crystal which is used in the spectrometer, this counting in place of costly item. The costly laboratories they have. The detector crystal is now called bismuth. Bismuth germanate. Bismuth germanate is a crystal which I have Vi, bismuth 4, germanium 3 and oxygen 12. This is a new crystal, costly crystal, which is used now in the laboratories in place of sodium iodide, etc., etc. Bismuth germanate, because bismuth, you see, has got Z atomic number 83. So 83, iodine was 53, germanium is low, no doubt, but this bismuth has, this is 32 probably Z, and this has got 83. So the presence of bismuth increases the increases the photoelectric effect probability or component probability or pair production. So this crystal is a costly crystal. This is available now in the modern laboratories. So in place of sodium iodide, in place of other crystals, we use bismuth germanate. Now what we have? I gave you, yesterday I gave you a block diagram of gamma ray spectrometer, in which first item was crystal sodium iodide hermetically sealed coupled with photomultiplier tube. So photomultiplier tube has got large number of high resistances. They are at the base, its circuit is made, so they are connected at the base. And then after the PM tube, in the same circuit we introduce electronic circuit. After that, the pulse of the scintillator sodium iodide anode is fed into a circuit known as preamplifier. So preamplifier is an electronic circuit designed such that you may have a transistor connected in common base configuration. So it is not an amplifier, it's a preamplifier, its amplification factor is nearly 1. It is not amplifier. It is a preamplifier, but what is its use? This is circuit just like a common base transistor connector in the input and output. You see what we have? We have a PM tube. This has got high impedance because it has got in output high impedance at output. Because it has high resistance, so many resistances. Those resistance R1 etc. were around 500K or 400 or 300K, and the other resistance R was say 1 mega ohm or 10 mega ohm. So this has got a high impedance at output. And we need, this is the pulses of millivolt. So we need a large pulse to count. A small pulse we cannot count, large error. So we use an amplifier. Amplifier is a device at the input here, suppose, and this is the output here. We connect this directly to this, so that this pulse goes here, this pulse of this side. What may happen? This pulse may get attenuated here, maybe like this, or pulse shape may change. Why? Because amplifier has got low input impedance. This has got high output impedance. So two impedances, one is high, one is low. If connected in parallel, what will be the result? You can see that you have two impedances. One is and in parallel, other is small. So one is R, very large, one is small r. To combine them parallel, find out the result. Result will be less than this is smallest. So if you combine 1000 ohm with the 1 ohm, you will find resultant less than 1 ohm. So high impedance and low impedance coupled in the parallel, the resultant impedance is lower than this impedance or this impedance. This is a R. This is a capital R. So we cannot couple a high impedance to a low impedance. This is called impedance mismatching. So then what we need in between amplifier who has got low input impedance and this has got high impedance, we put a circuit in between these two here, and the circuit is produced such that this has got here. This is high impedance, so here also this has got high impedance. And on this side, this has got, this is low, so this is coupled to this also has got low. To couple a high impedance photomultiplied tube with a low input impedance amplifier, we need a circuit which has no amplification, which has impedance matching. So this is called impedance matching. So preamplifier, this is a preamplifier. This is impedance. This is used for impedance matching device. To couple a high impedance circuit to a low impedance circuit, we use a circuit just like a common base transistor that has got input impedance here high. So these high and high took parallel combination of say high and high. This is no. So this pulse here is transmitted here as such, like this. No attenuation. Pulse from here to here. If pulse is changed, if pulse shape is changed, you will lose the information about the gamma ray energy, because pulse height is obtained from energy loss of gamma ray. So energy of gamma ray is built in inside the pulse height. So pulse height is proportional to energy of gamma ray. The energy of input gamma ray. So this, if you lose the pulse height, if you lose the information, if you get this pulse attenuated or change of the shape, you will lose this EI. Our aim is to get EI measured accurately, and hence we have to couple a high output impedance photomultiplier tube to a low input impedance amplifier using a impedance matching circuit, which is called preamplifier. This is just a common base amplifier transistor circuit. You can design very easily and can make. So this preamplifier is an essential unit. Preamplifier is the essential unit between. And what is amplifier? Amplifier, or it is for linear amplifier. This means this is to amplify millivolt pulses to few volt. So this amplifier has got cascade of amplifiers. You have common emitter transistors connected, several common emitter transistors connected together in series. So one emitter, first amplifier has say amplification factor 10, and 1 volt pulse gets multiplied by 10, so 10 volt, the next 10 to 100 volt, and next is 100 to 1000 volt. So you can have 3 stages, you can have 4 stages, you can have 2 stages. So you can have several stages of common emitter amplifiers connected together, so that we get a millivolt pulse amplifier to volt. This pulse can be detected by our electronic devices. So millivolt pulse, which is obtained from scintillation head, is converted into volt pulse using linear amplifier. So linear amplifier very easy to design. Electronics people can design. A student even doing PhD can design a little amplifier and make circuit. So this is pre-amplifier, amplifier. After this we have another unit which I gave in the block diagram. This is called pulse discriminator. Or pulse height analyzer. Pulse discriminator, because after this amplifier we have pulses of several pulses of different height. You have pulses not of 1 volt, because by Compton effect we have electrons of various energy. So each electron of energy is giving pulse of different height. Scattered gamma ray, Compton scattered gamma ray, lower energy gamma ray, they give lower energy electrons. So we have a distribution of large number of electrons having various kinds of energy, and these electrons produce electrical pulses of various different heights. And hence we don't have only one pulse of photoelectric effect. We have several pulses. Means this is not only one. This varies from one value, lower value to higher value. And we cannot count them by easily. Now we can count. Earlier, when I was a student, it was not possible to count because we were not having MC at that time. So, pulse height analyzer or pulse discriminator is a circuit which counts or which gives output. Input is here, all pulses V1, V2, V3, etc. Here we want output pulses only between V and V plus dV. Well, dV can be with any value, 1 or 0.1, whatever. Means V, if V is 1, you are counting pulses of 1 to 2 volt. V is now 2, you are counting pulses between 2 and 3 volt, like that. If V is 3, so you have discriminators, potentiometers, you can set them at different values so that you are allowing pulses of V and V plus dV. And this V can be changed to any value, 1, 2, 3, 4, 5, 200, millivolt, or whatever unit. And dV can be fixed. dV can be 1, 0.1, 0.5, whatever your desire. So this pulse discriminator or pulse height analyzer or single channel, single SCA, single channel analyzer. At one time, pulse of one particular height having some variation, 1 to 2, or 1 to 1.1, or 1 to 1.2, whatever you can decide this width. So a pulse of having width dV and initial value V can be counted. So we have some logic circuits here, with one logic circuit operates at one particular voltage, your bias the transistor such that no output after the pulse height is more than V, or second you can have no output when pulse height is more than V plus dV, and one you can design logic circuit and no output when pulse is less than V. So we get output pulses between V plus dV. We can design. We have circuit diagrams, we can design easily a pulse height discriminator or single channel analyzer. So pre-amplifier, amplifier, pulse height analyzer, and then we have an electronic circuit known as scaler. Scaler is a counting device where we can count pulse one by one. Earlier they were mechanical counter, now we have electronic counter that we count when 10 pulses come, next we pass, next it comes now 1. Then 100 pulses come, we pass to the next. So we have decade scalars, 10, 10, 10. If 10 comes, then it is 1. 100 comes, then it is 1. So next is 1000. So one single, 2 digit and 3 digit, and then we have mechanical recorders. So these scalars are electronic circuits which are used in the laboratories for the counting pulses. Electrical pulses counted by one. Earlier we were having binaries, now we had 10 digital decade based on 10. And scalar based on 10 means 10 pulse comes, then we get 1 pulse. Next stage. Earlier it was binary 2 to power n. So we were having 256 counter, 512 counter, 1024 counter, like that. So in place of this scalar and in place of this SCA, in place of this all these SCA etc., now we have after amplifier, we have directly connect to MCA, that is multi-channel analyzer. Means we have now a computerized, we have a software which operates a computerized electronic circuit which has got multi-channels. It was single channel one time, So it means you can have several thousand channels, single channel connected together. We have 256, 512, 1024 like that, 4096 and more than that, multiple of 256 like that, binary. So that has got multi-channel means at one time you can count all these pulses that we have in our laboratory, suppose 4096. Each channel giving you one pulse. Earlier we were having single channel, so each channel was counting one pulse at one time. So we were taking suppose 1 hour or 2 hours in counting our whole spectrum. This will give the whole spectrum in 100 seconds or 200 seconds. So earlier we were using whole day, 2 hours, 3 hours, 4 hours taking counting the whole spectrum. This gives in one run. One run you can count that each channel is counting one pulse and we get the whole spectrum. So multi-channel analyzer coupled with the PCs is now being used in all the laboratories to detect the gamma ray spectrum. But what is the gamma ray spectrum? Gamma ray spectrum, you see, I take example of, I have a cesium-137 radioactive isotope. This gives gamma ray of energy 662 keV. I put this source on the top of the sodium iodide crystal and then I get finally the electrical pulse after pulse discriminator. I count the pulses, what I get? I get a curve. This side channel number or connector, this is converted to energy also. And this side number of counts upon time, means counts per unit time. I will get some curve like this. Well, this curve is here. This is the 662 keV gamma ray. This is by photoelectric effect. So I get, this is having natural bit here, delta E, and this is the energy E, 662. So this is the photoelectric effect P. Photoelectric P I get monoenergetic because the total energy of gamma ray is converted into kinetic energy of electron. So we get one pulse. And this different broadness, I also explained you, is the statistical variation at different stages of counting. So we get by the same gamma ray pulses of this height, pulses of this height, pulses of this height, a variation. Otherwise, theoretically it should be only one way. And this is called X-rays. We get X-rays from cesium source where electron comes down to lower state. There is barium isotope, cesium decays to barium. We get barium X-rays of 32 keV around. So this, many times we don't see this because it is lost in the noise of the amplifier. And this region here, this region is called Compton region. Because by Compton scattering we get electrons of various energies scattered in different directions. So we get electrical pulses of different height. So Compton scattering doesn't give a peak of one height because it has variation due to scattering at various angles theta and phi. So we get this whole region. This is called Compton region Sometimes we get here a small bump here. This here, a small bump, is called some backscattering. Gamma ray scattered the backside from the material surrounding the system, surrounding the spectrometer. Backscattered gamma ray has generally constant. As I told you, the high energy gamma ray, backscattered gamma ray energy was 0.25. Last time we said 90 degrees scattered was 0.5. So most of the time, this is a small bump due to the backscattered gamma ray. Gamma ray energy is much more than less mass of energy of electron. So we get this backscattered peak. So this gives you a gamma ray, a spectrum of monoenergetic source, 662 keV cesium. Like that we can have some other sources, also a spectrum, and we have say a cobalt 60 source, cobalt 60 source. This gives 2 gamma ray, 1.17 MeV and 1.33 MeV. These 2 gamma rays. So here, this is two gamma rays, 1.33 and 1.17. These are photo peaks. This is a Compton region, this is a backscatter region, and X-ray is not visible. It is lost in the amplifier noise. So, like this we can see how many gamma rays coming out, and we can identify each gamma ray. But remember that this must be small. Otherwise, if any gamma ray is lying, say very close here or here, these gamma rays will come within this envelope, and we cannot separate them. So this delta E over E is an important factor, and this should be minimum so that you have good spectrometer. Like this, you can have peaks of various gamma sources. One more thing I want to explain, that when a gamma ray energy is say larger, maybe around larger means large, maybe say 3 MeV, maybe say 2.5 MeV. What happens? When this gamma ray is coming, when this is counted by photoelectric, there is no problem. But when this is having pair production inside, what will happen? That this is having a pair production here. A E plus and E minus is produced here with kinetic energy, and these combine together, annihilate. When they annihilate, we get a gamma ray of 0.511, a gamma ray of 0.511. Suppose this gamma ray is converted to electrons, it goes inside. But this gamma ray goes out. It is not available, its energy is lost. So we say this, the total energy of gamma ray is not counted, not converted into the number of electrons here. And gamma ray 1, this is called 1 gamma escape. So if you have the energy more than the energy required to produce pair, electron positron pair, like this energy, say 0.511 is lost. This is called 1 escape, 1 gamma escape. 1 gamma is going out. It is possible that the pair production takes place somewhere here, E plus and E minus, and we get gamma rays 0.511 going like this, outside the crystal. So 0.511 means both the gamma rays going out, 0.511. So what happens? This is called 0.511 plus 0.511. This is 2 gamma escape. Means 1.022 MeV energy is lost. It is not counted. It goes out. It is not going inside the system. So what we get, if we have this energy which is having pure production, we will have, in addition to photoelectric effect of this, which is very small, we will have gamma ray in the spectrum E gamma. We will have gamma ray E gamma minus 0.511, the energy peak. We will have peak at E gamma minus 1.22. So if a gamma ray of high energy comes, we get a spectrum, automatically we get many peaks. This doesn't mean that we have many gamma rays. This is the E gamma. So we have here this is total E gamma. Whatever. This is E gamma minus 0.511. This is E gamma minus 1.02. So we have only one gamma ray of energy, E gamma, but we are getting 3 gamma photo peaks. Why? Because 1 gamma escape or because 2 gamma escape. These gammas which are produced by electron-positron annihilation, mass annihilation, electron-positron kinetic energy available inside the crystal. That gives the electron, but the rest mass energy goes at the 2 gamma outside or 1 gamma outside. So that energy is not available for counting, and hence we, from 1 gamma ray we get 3 peaks, and these 3 peaks are not the 3 gamma rays, but we have to be careful that if we have a gamma ray of high energy, we will have in our spectrum 1 escape gamma and 2 escape gamma peak also. So this is to be remembered in our mind, that a single gamma ray energy can give you 3 peaks. So friends, I will stop at this place today, and when we meet again tomorrow or next day, we will discuss further, because this is the sodium iodide, has got poor resolution. I will explain how to minimize the delta E, how to make pulse sharper. So what are the methods used for increasing the resolution, resolving power of the spectrometer. So thank you very much for listening to me.